Okay, so we'll welcome everybody out to this webinar. This is a joint PICUP ALPhA webinar. And hopefully we've got some people who don't usually come to these things. So I'm Nick Nelson. I'm a faculty member at California State University, Chico in far Northern California. I guess I'm doing the introductions. So today we're going to hear from Tom Smith and Dave Vernier, who are both at Vernier Instruments. They're going to tell us some fun stuff about using Python to access some of their company's sensors, which I know we use at Chico State in our intro labs quite extensively. A couple of housekeeping items before we get going. We'll just remind folks to please try to keep yourself muted unless you're trying to talk. And please don't be offended if you get muted by myself or someone else if you forget to mute yourself. If you do have a question or something you'd like to ask sort of on the fly, we'd ask that there's a raise hand button. If you can use the raise hand button, that's a good way to sort of hopefully get attention without causing the verbal train wreck that occurs in Zoom when multiple people try to talk at the same time. Yeah, well, with that, I'll turn it over to Tom and Dave.
Hi, I'm going to start off. I'm Dave Vernier. I'm in Portland, Oregon, and I used to be a high school physics teacher and a long time ago. And now we make sensors for science teachers and mostly physics and chemistry. Anyway, I'm very excited about what we're doing, and we're excited you're here. And thanks to the PICUP people for having us to join this this event. I'll tell you a little history of this how we got involved in this. Like I say, I was a physics teacher, and back from even the Apple II days, I was interested in getting kids involved with learning a little bit of coding and just getting comfortable with computers. I even wrote this book back in 1986. Was Apple II projects. Kids would build little electronic circuits and then write little basic programs to do it. We've been continuing on with that over the years. We've written lots and lots of books of projects for kids doing various things. And we've done everything from Lego to Arduino to lots of LabVIEW. And we just keep, trying to come up with ways for people to teach a little bit of coding in their physics classes, and also use our sensors. And why do we do this? Well, because I think it's educational for the kids to get involved and learn a little bit of this. We think it's great for projects, and frankly, we just think it's a whole lot of fun. So that's the history. Early on, we've been, like say, doing it for a long time. I went to a PICUP workshop at an APT meeting, probably maybe 4 years ago, pre-pandemic, and I was really impressed with what you guys were doing in computational physics. And it jumped out to me, boy, wouldn't it be nice if we could not only do the modeling stuff, but then take real data and compare the real data that you take with our sensors with what you do with your computational physics stuff, even simple things like falling objects and subharmonic motion and stuff like that. But unfortunately, at the time, we didn't have a great system for doing that. We could do it with some of that with LabVIEW, but LabVIEW is expensive and all that stuff. And then we came out with a whole line of new sensors about the same time. These Go Direct ones, these are wireless and Bluetooth. And we were able to, not thanks to me, but to our team, they were able to put support in for getting Python to work with with the Go Direct sensors, and like 35 of them, you can read them either by USB or Bluetooth. Well, that was really cool. And we did a lot of work with that. Tom's going to demonstrate some of that. And then, but that was Python without the graphics and all. And now that we we started playing with VPython installed version, and we found a lot of trouble getting the installations going. So we never really jumped on this. And then we had a lucky break of Bruce Sherwood moved to Portland, Oregon. That's where we are. And we got to know Bruce better. And he was wonderful to work with us. And he said early on that he thought he could show us how to make these wireless sensors and Bluetooth and also USB work in Web VPython. And that's led to real excitement about this thing. We'll demonstrate some of that too. So we're going to demonstrate both the installed and the Web VPython as part of this thing. So I'm very excited about what we're doing. I'll demonstrate a couple things later, but I'll let Tom show you some of the stuff to start with.
Great, thanks, Dave. I'm going to go ahead and share my screen and just kind of show you some of the resources, where to go if you want to check this out, and then show you a couple of examples. So we'll get started with that. It's always a challenge to figure out how to share your screen, but I think I've accomplished that now. So it's our website. I'm just going to search for Python here. And on the search button there. We're thinking about it, and now we'll go to Python and Vernier sensors, which is our landing page for these resources. A little information for somebody who may not be familiar with Python, why do we want to do this? And then here's where the tools really start. So this is Python that you have installed on your computer and Go Direct sensors. There's a guide there. I'll take you to one of these guides here in a moment. Then there's a section on Web VPython and another guide. And finally, a third section dealing with our LabQuest sensors, which are the wired sensors, and its own guide. We kind of parsed it out this way because there are different libraries associated with the Python and LabQuest sensors versus Python and Go Direct. And Web VPython is its own little animal there as well. So let me just show you, if you go to the guide, it basically takes you to a web page, getting started web page that's hosted on GitHub. And there's a good amount of getting started resources for if you're not familiar at all with installed Python, which I assume most of you are. This is a good place to go because it tells you how to download Python and install it and install our library so that you can access that, and has a lot of good troubleshooting guides in there as well. And then once you've kind of gone through that process, or maybe you can skip that altogether if you're already there, you can just go and view on GitHub. And on GitHub itself, we have JavaScript, Python, and Web VPython. And we're really looking for, you can download example code by downloading the repository here. But again, this is kind of a getting started, similar to what we've seen out there earlier. And then you can download, take a look at the Python examples here. And in our examples, we have Go Direct. GDX is our shorthand for Go Direct, the sensors that Dave was referring to. We have another set of examples for VPython there as well. So that's just kind of where the resources live. I'm going to move away from the website and just kind of launch a couple of examples to show you kind of what we have available to you. So the picture of a LabQuest sensor here. So this is just a pressure sensor with a syringe attached so that we can easily manipulate the values going into a LabQuest Mini that's connected to our computer. And then this is our Python code, just using idle for the sake of simplicity to show you the code here. So we have a library called LabQuest that we've imported, and Sam Swartley also included a logging tool for some troubleshooting there. All of the calls for different functions within the LabQuest library are abbreviated with the LQ. And so we have, we open up the sensor, we select a sensor out of channel 1 on our LabQuest Mini, and we set a sampling rate. So that's the setup part. And then we just go in and take 10 readings for this one. The important part here is that we have specific code to both stop data collection and to close our sensor so that everything shuts down appropriately, and then start the sensor. We've tried to make these calls, regardless of whether we're in Web VPython or an installed version of Python, using our GoDirect sensors or LabQuest sensors, to be very similar. So we've tried hard to standardize that. And here's our code. We're just going to take the red, green, and blue readings from the code and adjust the size of the boxes, and then kind of reverse engineer the color to recombine the individual colors to make a single color. So this works a little bit differently in Web VPython, where you go to the share. Let me go back to this. Go to share or export the program to download it as HTML, because you're dealing with sensor data on a website. So there's some security factors you have to consider. And then if we just open that up, we get this same platform here with a graph. Here's my 3 boxes for a red, green, and blue color. And this larger box that we're going to match the color of what I'm showing on the screen here. So this connect to my GoDirect sensor. And again, I get these collect and close buttons. I get some live readouts from my sensor. Let me pull the video back up on top here. So I can, here, I'll put this. So basically I have some colored paper underneath that. And if I hit collect, it matches, you see a live readout of the graph. This tells you what sensors are connected and matches the colors. So we basically made an algorithm to read the 3 sensor readings and then recreate a color. If I change the color, it's kind of green and so forth. So this is an example of something that you really can't do in regular data collection software. It's kind of a unique aspect of being able to play around with Web VPython, where you can be creative, bring in your own influences there. And then when you're finished up with that, again, we have the stop and close buttons to shut down everything appropriately. I'll note that there's also this, you can change the sampling rate of the sensor embedded in this program as well. So those are all kind of standard features of the Vernier VPython canvas. Go ahead and close that. I'm going to show you one more example before I turn it back over to Dave. And we're gonna just change this a little bit here. I'm going to change my camera view to a cart and track. This is one of our GoDirect carts, so it has sensors embedded in it. And I'm just using a plunger on the other side of it to basically launch the cart. So look at that there. We're going to basically do a little experiment with a constant acceleration model. So let me bring up that program. So go back to my list of programs. And we're going to open up cart on a ramp with data. So again, there's our library call. I've made a ramp and a couple of balls. One is a model that I'm going to manipulate with calculated or model values for acceleration and velocity, initial velocity, and initial position. And then the other is going to be actual data collected using the GoDirect sensor embedded in the cart. So this is using a position sensor that happens to be sensor number 1 on the cart. And there's some more setup here with the canvas, a little bit of setup with to get the data from both the model and the sensors in the setup. And then we'll just collect some data using this. So once again, we have this kind of interesting process where we say share or export and download HTML. And then here's the program to run. So we'll launch that. And we get this screen here. Let me just see if I can make this a little bit larger. I can grab the corner here. There we go. Okay, so I'm going to click select device. I need to make sure that my sensor is on. So it'll find it. And of course, here I am at Vernier. So we have quite a few sensors. There is my cart though, right there. I'll click pair. This is using the Bluetooth connection because you don't want a wire attached to this thing as it's going up the ramp. And then I'm just going to go ahead and I'll hit collect, which will start the model. And then I'm going to release the cart, hopefully pretty close to the same time. I almost need a lab partner for this, so we'll get that going. And I've set this up so that the data stops collecting when my model has come back to the beginning. So you can see our model doesn't quite match up with the reality of this particular setup. So at this point, your students could manipulate their model to check that out, or do the reverse, maybe change their physical setup to match their model more accurately. Just a couple of examples here. So I'm going to turn it over to Dave here to show some more examples. But first, I need to stop sharing my screen. There we go.
Thanks, Tom. Tom always does a good job demonstrating those things. I guess I want to stress that he showed both our old sensors. They're not old, that we still sell them, but some of those sensors. If you bought a sensor in 2008, you can use that thing with Python, the wired sensors, and then the GDX sensors you can use either with installed Python or with Web VPython, and you can use them by Bluetooth or by USB. So that's pretty cool. Another thing, this may not be a big deal to college instructors, but it sure is a big deal to us because high schools are very much dominated now by Chromebooks. And the wonderful thing about one of the wonderful things about Web VPython is we can use it with Chromebooks. That's the only way. Well, we have our own software for Chromebooks, but you can't do installed Python with Chromebooks with our sensors anyway. So I'm going to show a couple demos. These are all Web VPython demos, and Tom showed sort of the basic starter programs mostly, that one cool one with the color. But I'm going to show sort of the more gee whiz things, showing possibilities. I've had a lot of fun with this. And first I'll show you one involving subharmonic motion. And behind me here, I guess I better start showing this here on my screen. Behind me, you might see I've got a mass on a spring. It's a ½ kilogram and it's oscillating up and down and above a motion detector, a GDX motion detector. I've actually got it connected by USB, but now I'll start sharing screen. So this is my Web VPython account. These, when you set up, you guys know this, but I think it's amazing that you get all this stuff stored on a server and you don't have to pay anything, and it's just a great service. I'm going to run a program called Simple Harmonic Motion here. I'm not going to run it. I'm going to open it, but I can't run it. Remember, this is we're using sensors, so we can't just click on run. We have to, as Tom showed, we have to do this, and we have to do downloads H2ML. And I don't know why mine is not showing up down here like it used to, but now it's showing up here. It's in your downloads folder too, you know that. If I run this, now this is kind of a little more bells and whistles. We've got the button here for select to go direct sensor. So we choose that. I've only got one plugged in, so it shows up, and I make a connection. And I guess I'm already moving. If I hit collect, we get a pretty nice graph of the motion. I've added bells and whistles here with the arrows for the velocity and the acceleration. You can do this kind of goofy stuff, but I think it's almost like science fiction. And I've even added a thing here where I can click on that and add a model. And that model is built into the program. I'll show you where that is. It's right at the top of the program. So the idea is that the students could experiment with that and change. And this is legit real data. I did actually measure the spring constant, and the mass is really a half kilogram. It comes out pretty darn nicely. So I think this has got great possibilities, and it's kind of a cool thing to do. I'll show a couple more here. This one is different, a different thing. This is going to be an example where we're not using our sensors, at least not at the moment of the data collection. Here on, let's see, the color, let's see, oh, wrong tab. Notice we have tabs here. I want.
Dave, can I interrupt you for just one sec? There was a question in the chat. I'm sorry, I still haven't re-enabled everybody's ability to.
Yeah, that's fine.
But the question was asking, it says, I may have missed it somewhere along the way, but can you use non-go direct sensors through an interface like LQ2 attached by USB?
The answer is yes, in installed Python. And even you can even add, do that with, well, you could add some graphic elements, but you can't do it with Web VPython. And that's what Tom demonstrated. The very, very first thing he did demonstrate, it was a little disrupted, but that was using a wired sensor. You were using a LabQuest Mini, but it could even be an old LabQuest 1 even, but any LabQuest works. Okay, I'm going to go ahead and do this demonstration. Now, this is one, we have a lab in our advanced physics book where we have the kids use this kind of paper. Most of you have seen this lab. You go around, you put a potential, like often you use 2-point sources or 2 plates, and you apply 5 volts or so, and then you go around with some kind of voltage measurement system, and you take readings at a whole bunch of places, and then you plot the electric potential. Well, we used to tell people in our book to do that with our software, but then to plot the data with Excel, because we didn't have 3D plotting in our software. Well, we still don't, except that I wrote this thing, and it's been kind of fun. I'll show you. So this is going to import data, not take the data on the fly. So I'm allowed to do this. Click here. It's a little slow to open because there's a lot of data. So the model is now you use our graphical analysis program to take the data, but then you save it as a CSV and then you import it. And then you get, then this program does the job of the plotting. And, it does kind of a cool plot. the black dots are the readings that the people made, and you get that kind of effect. So anyway, I think that's kind of fun. And again, I was able to run it because it didn't take the data at the time, but we actually import files. I'll do one more here. If I go here, this is literally what I've been working on today, but I think it's got possibilities. In computational physics, one of the classic demo that people like to do is free fall with resistance, because you know, there's not a real good analytical solution. So we have a lab in our basic physics book where we drop coffee filters, and we've had that for 20 years at least, probably 30 years. But I just took the data. I didn't actually take new data. I just exported data from graphical analysis, our program, by CSV file, and I wrote a program here that will let me read that and then plot the data. So this is my program. It's not much of a program. It's just going to read the file, and then it's going to plot a graph. In fact, two graphs, two lines on one graph. The real data that was imported from the file, and then a model based on simple, you know, a model using the data right here in this area. And again, I put this near the top so the kids could change it, easily find it, and experiment with it. And this is what I've been doing today. So if I run this program, now I can actually open a file, and I'm going to bring on the data for one single filter. That's, you know, it's very light. I actually weighed this thing. It's about 1 gram. So if I run this, now I experimented with this model until I got it so that remember, the red is the real data, and the blue, I don't know why that's not got the good twist there at the end, but I played with I did the model with the drag proportional to the square of the velocity. And I played with the numbers until I got about that, you know, roughly the same slope at her terminal velocity part anyway. And then here was a fun thing I experimented with. In our lab, what we have you do is nest together more coffee filters. So the most we did in the actual data I have in the sample file, we have 5 filters nested together. And so I went in here and changed the program. So the surface is not different. The drag area should be the same. So if I just change the program to make the mass 5 times bigger, we should be interesting to see how the comparison comes out. So I'm going to run the program again with this slight change. And now I'll choose file. This is the data I exported with 5 filters. And you see, it actually is coming out fairly parallel again. So I guess it's an example where I would argue that we kind of made a model, and we showed that the model actually worked to predict something in the future, or show a pattern at least. I guess that's the main things I want to show. I'm going to stop sharing and just say a few words. I think this stuff is amazing. I again thank Bruce and his wife Ruth. They have a whole book where they make using computational physics, a big part of it, and that's been an inspiration to us. I think one of the neat things about this webinar is, like I said before, you can use almost any sensor that you got from us since about 2007. And the other thing is, the neat thing is, all this stuff is, all the software is now free, and even you don't have subscriptions, and it's really quite amazing that you can do this stuff, and it sure is fun. Do we have other questions we should answer?
Okay, I'm going to try to re-enable people unmuting themselves, and hopefully we've gotten everybody at this point. So let's make sure. Okay, so folks, you should be able to unmute yourselves now. So if we have any questions, you can always just put them in the chat, but if you'd like to actually unmute yourselves and ask it in person, you can.
Is there any possibility of like running control back? You know, like having a responsive system where it would maybe be able to control the experiment?
We have one product. I think I've got one. No, I don't. Something called a digital control unit, which is is not wireless and it's not go direct. So it would have to plug into something like a LabQuest 2, and then that you could control in installed Python. That's all. We hope in the future to have some kind of wireless go direct control device.
Thank you.
I have a question. I might have missed it at the beginning, but when you were searching the Vernier website for, you know, just to get started to find all the Python repositories, files and such, was there, do you collect, I guess, code from other sources that maybe like instructors have contributed that they'd like to share?
Tom, you jump in if you want, but I think the answer is we have not yet. We might in the future.
I guess I'll just jump in a little bit, Dave. We're curious as to how you would see this being used in your labs, in your coursework. And, you know, we're actively making programs that we think are interesting, but we're a little bit removed from the lab these days. So if you have ideas or programs that are working for you, we'd be glad to see them and glad to know what direction you're going with this type of idea.
Well, I've certainly been looking for ways to incorporate either live or recorded data. I take my high school students through a little set of tutorials for using what is now Web VPython, and it kind of comes to somewhat of a halt after you do your basic mechanics stuff. And I would like to extend that and continue on. And I'm thinking about ways that we could use this to like maybe visualize some electric field stuff, or I'm just barely thinking about this yet at this point, but this demo's got me thinking about what could I do with this in the other parts of my course besides just basic mechanics and kinematics.
Yeah, and you know, we don't pretend to have all the answers. We're looking for things that we can show off that are kind of cool. I think that thing Tom came up with the color is a really cool example. And for me, this is just me, but I think I've been doing coding for 50 years and I like doing it, but it's more fun if you can make something react with the real world, either, you know, take readings by moving something or pushing, you know, some kind of input or even better output too. I think it just makes the whole concept of learning programming more fun, and you introduce new interesting ideas. I'll say I absolutely think this stuff is wonderful for projects, and you know, we think we write very good software, but there's no way we can write software to do every project that you want to do. You sometimes need to customize things, and that's what this is all about.
If some of you aren't watching chat right now, Robert had a comment about running a simulation and then comparing with real data collected side by side would be helpful. And one of the things I've been thinking about is a kind of an extension of what we showed you today is maybe just simply putting a button or a control device on the front page of Web VPython so that you could change the variables in your model to more accurately match up with data, just to make it a little bit more easily interactable.
Yeah. I've chosen to do it the other way, would have the kids actually change the code, because I thought that I'm trying to teach coding at the same time, but certainly it's doable to put sliders for all these variables, and that makes a great, if modeling is your main goal, that's a great way to go.
I think I should comment for those, there may be people who are not familiar with this, but if you go to webvpython.org, webpython.org, you'll find there that you can, without subscribing or anything, you just have to get a Google account. There's abundant documentation there on how to write VPython programs. And what Vernier has done is to make it really easy. Well, it's already very unusually easy to make 3D animations in a Python program at webvpython.org. That's sort of unprecedented in a way. But what they've added is the ability for these very short, rather easy to write programs to access their sensors. And that's a huge step forward. But I just want to make sure that if you've never heard of webvpython, you might not know where to go to find this thing, and that's what it is.
Yeah, and most of the thanks for us getting this going is to Bruce, who just spoke. Also, Tom, we haven't mentioned where you can get, you mentioned briefly, but I want to stress again that there's a lot of materials. The stuff on the Web VPython page is absolutely wonderful. Their examples are amazing. And they're great science things too, like the hard, models for gases and stuff. But we have on our, if you go to the website, you can download a getting started guide for Web VPython with our sensors. And then there's a much longer document that's got more details about all the functions and how it works. So there's great stuff. And then of course, there's wonderful videos out there with people like Rhett Elaine and lots of others who've just done amazing training videos on Web VPython.
So there's a question in the chat that says, I've used Web VPython, aka Glowscript, but my school is moving away from Google. Is there a Microsoft login? I think you just need a Chrome browser to type in Web VPython or glowscript.org to access that. Bruce, do you have anything?
Yeah, I should respond to that. Yes, that is a problem for some institutions, and this is a problem for some people in Europe. There is so the problem is some people feel skittish, and I can understand that, of having to use have a Google account or be able to log in at python.org. So the problem is that the machinery is based on the Google App Engine machinery and its associated data store, which means that there isn't a way around at the moment having to have that login, except there is a not very good offline thing. If it went to python.org, the documentation will tell you how to get this. There's a zip file you can download, open it up, and it'll run without being connected to the internet, let alone not having a Google account. It's not very good. I'm not very proud of that version, but I know of at least one use of it, which is in China, where an Australian teaching in Shenzhen, one of the big industrial cities, teaching in an academy there, the students don't have access to webvpython.org. And so he has them use this downloaded version, which breaks that problem. The better news is that Steve Spiegelmeier is a co-developer of VPython, and he's a very powerful programmer. He can do things I do not know how to do. And he's been looking seriously into the possibility that the storage of your data need not be a Google cloud place. and that he thinks he could be able to pull off a version of Web VPython where it could be your school server where the data is held. And that would solve the problem that some people experience. On the other hand, I will comment that it was even tougher to use Python itself in an educational institution, because IT would not allow you to install Python because it was open source, which was known to be extremely dangerous. Well, we got past that.
Hi, this is Anthony Esquadro again. So we're at 7 o'clock, and I want to be respectful of people's time. I think we've all had kind of quite the experience today. So I want to thank Tom and Dave for their patience and their grace under pressure, and bearing with the difficulties today. Especially also want to thank Nick for managing as best as he could to manage the disruption. I don't know if there Dave and Tom, after tonight's events, are you still willing to stick around, or should we call it a night?
No, I'm happy to stick around.
Yeah.
I guess we did the right thing. We didn't give them much reaction, and that's probably what they wanted was reaction. So.
Yeah, of course. Well, so yeah, Dave and Tom is graciously been willing to stick around for a few minutes if there are questions. It might take some time for us to get the recording up. It's not just going to be slapping on YouTube as usual. So, but yeah, thanks for everyone for bearing with the events of tonight. And yeah, we'll try to look into what we can do so that this doesn't happen again. Thanks again.
I might add one thing, Anthony. We did a very similar version of this webinar about a week ago. And at least the part where Tom did all his stuff where it was most disrupted, that is almost the same. It was almost the same spiel, that part. And we'd be happy to share that with you. I know, I think it would fit in. I mean, we wouldn't try to trick people. You could just say pieces of this were taken from this other webinar if you want. It's up to you.
Right.
Oh, that's very kind of you. Thank you.
Yeah, Dave, I think that would work well if you can get that to.
I don't think it's been posted yet, but they recorded it and they promised me they were going to post it.
Yeah, if you could get that to us, we'll edit this version and then we'll put that along. We can post.
Well, Tom was in the same room. I'm in the same room. Yeah. It's just as messy now as it was then.
Yeah. If you can get that to us.